This aircraft shouldn't exist. To lift 75,000 pounds, that's 34 metric tons, of dams and cruise missiles, plus full fuel, the wings need to generate enormous lift at takeoff speeds around 160 knots. But the same wings must slice through the air at Mach 1.2 without creating a wall of drag that would suck the engines dry. For 50 years, every fixed-wing design hit the same physics wall. The lift equation is merciless. L equals 1/2 rho V superscript 2 S Cn square L. Double the weight, you need double the lift. At low speed, you have almost no V superscript 2 to play with, so you need massive wing area S and high lift coefficient Cn square L. But fly that same huge wing supersonic, and wave drag explodes. Shock waves form, boundary layer separates, and your bomber becomes a flying anchor. That's the impossible barrier the B-1B was engineered to break. Map of Operation Epic Fury strikes deep inside Iran. B-1B routes from RAF Fairford or Diego Garcia. 30-plus hour missions. Overlay, why Iran needs precision mass, ballistic missile sites, C2 node refineries. March 2026. Operation Epic Fury. The United States needed to reach targets inside Iran that fighters can't reach without tanker support for days and forward bases that are politically impossible. One platform could do it. A bomber that carries the largest conventional payload in the Air Force inventory, officially 75,000 pounds per aircraft, enough for 24 GBU, 31,000 pounds DAMs or 24 AGM 158 JSSM cruise missiles. Some headlines screamed 100 tons. In reality, that's a theoretical ceiling across multiple aircraft and multiple sorties. But even the real 34-ton loadout per plane is enough to shock any capital, because it arrives with GPS-guided precision measured in meters, not city blocks. Unswept wing at Mach 0.8, creating massive shock waves, red high-pressure zones. Right, same wing swept 67 degrees. Shocks delayed, drag drops dramatically. Graph, drag coefficient versus Mach number, showing the drag rise peak, that variable sweep flattens. Here's the first principles problem. At transonic speeds, the air ahead of the wing can't get out of the way fast enough. Local flow hits Mach 1. Shock waves slam into the wing, and drag coefficient can triple in seconds. That's why the original B-1A, designed for Mach 2+, was forced to trade away payload and range. The only way to satisfy both ends of the flight envelope is to change the wing's effective geometry in flight. Why? Because the component of velocity perpendicular to the leading edge determines when shock waves form. Sweep the wing back, and that perpendicular velocity drops. The same wing that gave you high Cn square at 15 degrees sweep for takeoff now behaves like a thin, low-drag delta at 67.5 degrees sweep for supersonic dash. It's not a gimmick. It's the direct mathematical consequence of the Prandtl-Glauert compressibility correction and the need to delay critical Mach number. Visual, exploded 3D model of the B-1B wing pivot. Massive titanium knuckle, hydraulic actuators, torque tubes. Cut to high-speed footage of wings sweeping in flight. Then rotary launcher animation inside bomb bays, releasing dams in sequence. Engineers solved it with one of the most complex mechanical systems ever put on an airplane, the variable geometry wing pivot. 2 giant titanium hinges per wing, driven by 4 hydraulic actuators, capable of swinging 200,000 pounds of wing and stores to a 52-degree arc in under 20 seconds. The pivot is so strong it can handle the bending moment of a fully loaded wing at 9G, loads measured in millions of inch-pounds. Inside the 3 internal bays sit rotary launchers, essentially giant revolver cylinders, that let the B-1B ripple fire 24 dams in seconds without ever opening external doors that would spike radar cross-section. JDAM itself is brilliant in its simplicity. Strap a $25,000 GPS/INS tail kit onto a dumb MK-84 bomb, and suddenly every 500-pounder becomes a smart weapon accurate to 5 meters. Cruise missiles like JSSM ride the same launchers, fire and forget, 500-plus km standoff range. The result? The B-1B can take off heavy, sweep wings back, dash at 900 miles per hour, then loiter or penetrate at low altitude using terrain-following radar. Physics says it shouldn't be possible in one airframe. The B-1B 1B proves it is. Visual, graph, payload versus range for B, 1B versus B, 52 versus B, 2. Fuel burn curve at Mach 1.2. Maintenance cost comparison. Animation, wing pivot mechanism where over thousands of cycles. But nothing is free. The sweep mechanism adds roughly 4,000 pounds of structure and hydraulics. Weight that could have been more bombs. Max speed was cut from the B, one as Mach 2.2 to Mach 1.2 to save structural weight and fuel. Every sweep cycle stresses those titanium knuckles. The fleet spends more time in depot than any other bomber. And while 75,000 pounds of damn sounds devastating, each sortie still burns 200,000 plus pounds of JP-8. That's why these missions require multiple aerial refuelings and cost tens of millions per flight hour when you factor in tanker support. Marketing videos love to show the payload. They rarely show the maintenance hangar full of hydraulic leaks and cracked pivot bearings. So, is the B-1B actually viable for the future? Yes. Not because it's perfect, but because it's the only airframe that can deliver mass precision on day one of a conflict without forward basing. In the skies over Iran in 2026, it proved the concept. Dozens of DAMs and JASSM per aircraft, delivered from 8,000 miles away, with effects measured in destroyed launchers and command nodes rather than rubble. Economically, each plane costs about $300 million today, but the fleet is already paid for. The real expense is the 30-hour missions and tanker fleet, still cheaper than losing a $100 million fighter and pilot to Iranian air defenses. March 2nd, 2026. 3 B-1B Lancers liftoff from Ellsworth AFB in South Dakota, heavy with fuel and weapons, headed for a 30-plus hour nonstop round trip to strike ballistic missile sites deep inside Iran. Operation Epic Fury has begun, but rewind 40 years. Engineers face a brutal physics wall that almost killed the entire program. To generate enough lift at 160-knot takeoff speeds with a 477,000-pound gross weight, that's over 216 metric tons. You need massive wing area and high lift coefficient. Simple, bigger wings, more flaps, higher angle of attack. Except those same wings must then accelerate to Mach 1.2 without the aircraft ripping itself apart from wave drag. At transonic speeds, airflow over a thick, unswept wing reaches Mach 1 locally. Shock waves form. Pressure jumps discontinuously. Drag coefficient can quadruple in seconds. The aircraft either stalls from shock-induced separation, or the engines gulp fuel, so fast emission radius collapses to useless. For decades, that trade-off was considered unbreakable. Fixed geometry equals compromise. Supersonic equals tiny wings, tiny payload. Subsonic hauler equals sitting duck. The B-1 program was canceled in 1977 partly because no one could solve it without bleeding performance at one end or the other, until variable sweep-proof physics could be engineered around, not broken. In the end, the B-1B is a perfect example of human ingenuity versus the laws of physics. We didn't break the rules. We just engineered around them, one pivot, one equation, one mission at a time. And Tehran just felt the difference.